Hi guys, in this video we are going to be summarizing the hazardous earth topic, and I've divided it into two parts, and part one is going to be on atmospheric hazards, and then the second video that we'll do on this will be on the tectonic hazards. So under atmospheric hazards, the first thing that we need to talk about are high and low pressure systems. So when do we get low atmospheric pressure then? So this happens when the air around the ground is warmed up by the sun. So as a result of getting warmed up, it becomes less dense and therefore begins to rise. As it rises, it's obviously taking away pressure from the Earth's surface and therefore creating low pressure. Now, as the air rises then, if we look at this diagram here, so the low pressure has been created here, and the air has begun to rise. And as the air rises, it's going to cool down and condense. And now we know that we lose 6 degrees Celsius per every 1,000 meters we go up into the atmosphere. And that is what leads to condensation. That condensation obviously forms clouds, and those clouds give us precipitation. Okay, then moving on to high atmospheric pressure. Now, this happens when air sinks, and the air sinks because it has cooled down in the upper levels of the atmosphere. So as it sinks, it exerts pressure on the Earth's surface. Now, that is what we are referring to here as high pressure. And that normally gives us fine settled weather because there is no condensation, obviously, and no formation of clouds. Okay, so high and low atmospheric pressure are what actually causes wind, or they create wind. So the wind is going to move from those areas of high pressure to areas of low pressure. And that's because as the air is sinking here in the anticyclonic conditions or high pressure conditions, it's pressing down on the air that is below it, and that air has to move somewhere. So it's going to move towards the areas that have low pressure. And that air movement from those high to low pressure zones is what creates the winds. In this second slide, we'll be talking about global insolation and temperature. So the sun is crucial to maintaining the balance of heat on the Earth, and it's what gives us the insolation, so it heats the Earth. And the equator is where we get the most insolation. Now, if you look at the diagram here, we can see that the sun is striking the equator the most directly at a 90-degree angle. And because of that, the equatorial regions are the ones that get the most intense sunlight and therefore warm up the most. And then as we move away from the equator into the higher latitude, so we've got 30 degrees there, we've got 60 degrees, and eventually 90 degrees at the North Pole, we can see that the angle of this incoming sunlight becomes a lot lower. And that sunlight, or those sun's rays, are traveling over a lot more atmosphere and therefore are likely to lose some of the heat as they travel through that atmosphere. So they do not heat up the higher latitudes as much as they do the equator. Now, that heat here on Earth then is redistributed by the wind. So we had talked about wind in the last slide, and we did say that the wind moves from areas of high pressure to low pressure, and that wind is going to redistribute this heat from the equator to the higher latitudes so that we can maintain the balance of heat in the atmosphere. Now, that air movement redistributes the heat around the globe through two main ways. So you've got pressure differences through those pressure differences we just talked about, and then ocean currents also redistribute the Earth from the equator towards the higher latitudes. So how do pressure differences redistribute heat around the Earth? Now, the land and the sea warm up at different rates. The land will heat up a lot faster because it mostly has darker surfaces which absorb heat, from the sun, and therefore in the summer it's going to heat up a lot faster than the water or the sea, and will also lose that temperature a lot quicker in the winter. So when the land heats up quickly in the summer, it warms the air around it, which then expands and rises. And we know that as air rises, it creates low pressure. And then on the part of the sea will actually reflect some of the sunlight, meaning that less of it is absorbed. And whatever is absorbed normally up to 30 meters depth. And therefore, it will take longer to heat up, but will also cool up a lot slower, or will take a lot longer to cool down. And therefore, in the summer, the air over the sea will remain cooler and denser, and will therefore sink to create high pressure. Now, if you look at the weather map that is on this particular slide, you can see that most of the high pressure regions then are over the oceans, and the low pressure areas are over the land. Now, that obviously is telling us what we've just said, that over the land, the air pressure is lower because the sun is heating up the ground and warming up a lot faster, and as a result there is low pressure because the air is rising due to warming up a lot faster. Then in the sea, it's warming up slower, and therefore the air is going to be sinking here. Now, the result of that is that those differences in pressure between the land and the sea will cause the air to move from those high pressure seas and oceans to the land. And obviously, as that air moves, it's going to redistribute heat across the globe. Okay, so how do ocean currents redistribute heat across the globe? Now, in the North Atlantic, the salty seawater is very cold due to high latitude. So this means that the areas in the North Atlantic are going to be closer to the polar regions, and therefore the air temperatures are going to be quite low, which then also means that the salty seawater there is going to be cold. Now, because it's cold, it's going to be dense, and therefore is going to sink towards the bottom of the ocean. Now, as this happens, it's going to create convection currents, and those convection currents are then going to begin to drag the surface water down to the bottom of the ocean as well. Now, if the surface water in the North Atlantic is being drawn down, then it means that water has to fill that space that is created from a different region. So that water will come in then from areas that are closer to the equator. And one such area is the Gulf of Mexico. So as the water will be drawn over the surface, obviously, towards the North Atlantic from the Gulf of Mexico. And we know that the Gulf of Mexico, being near the equator, is going to have water temperatures that are higher. Now, that water then will be drawn up towards the North Atlantic waters, causing warming of the water in the North Atlantic. So when that water then gets to the Greenland seas and the Labrador regions, as you can see here on the map, it's then going to be dragged down again. It's going to be dragged down again towards those equatorial regions, and then be warmed up again, and then be transported again through the Gulf Stream up again towards the North Atlantic, and then it will cool down again, and then it's going to come back again, be warmed up, and then it's, the cycle is just going to keep repeating itself. And as that happens, warm air is going to be moved from the equatorial regions up towards the higher latitudes. So an example of that happening is here in the UK and in Canada. So the area in the UK that we'll talk about is the Isles of Scilly. So these are 70 kilometers west of Cornwall. And in this area, the winters are much warmer than the rest of the UK. And that is because they are receiving the Gulf Stream or the waters from they are receiving the Gulf Stream waters. Now in the UK we actually refer to that particular mass of air mass that is coming into the UK as the North Atlantic Drift, which is actually the prevailing wind that is coming into the UK. And because it's coming from the Gulf of Mexico, it has a warming effect on the UK, and that's why the UK is considered to be a temperate climate where the temperatures are not too high and they're also not too low in the winter. Not too high in the summer and not too low in the winter. Now, if we compare that then to Canada, St. John's, Newfoundland in Canada is Canada's most easterly point. So that is around this Labrador region here, okay? And because of that, it then has the impact of the cold air that is being drawn down now from the North Atlantic towards the Gulf Stream, which means that the temperatures there are going to be a lot colder. In fact, this particular area averages 18 days of snow in January and average temperatures of -9 degrees Celsius. So this area is ideally 15 degrees colder than the Scilly Isles here in the UK, despite the fact that the two areas are at a similar latitude. And the reason is the Gulf Stream. So ocean currents actually do redistribute heat across the Earth, and they have an impact in the areas that they come across. Okay, so the next thing we'll talk about is the global atmospheric circulation. So this is the model that you can see here on the right, and it's also referred to as the tricellular model. And that's because it consists of 3 cells that redistribute heat from the equator. Okay, so we'll start at the ITCZ, and that is this area here near the equator. Now we can see that the equator is right there, and that there's low pressure at the equator, and that's because of the sun's heat. We said that the insolation is most at the equator. So the equator is the one that heats up the most, and as a result of that, the air warms up, low pressure is created, and the air rises. So as you can see here, this rising air, or the arrows are in red, meaning that the air is warm. Now, generally speaking, we will lose 6.5 degrees Celsius in terms of temperature as we go up into the atmosphere, which means that this air will cool down as it rises, and eventually it's going to condense to form clouds, and those clouds will give rainfall. Now, that rainfall obviously means that these equatorial regions are hot and wet throughout the year. So this air that is up here now that had cooled down and condensed, the air that is up here now is a lot colder, and because of that, it will then have to sink. Now, it will not sink back down to the equator because at the equator there is rising air that is going to block it from sinking down to the equator, and therefore the air is going to be drawn down towards the tropical regions, which are at around 30 degrees north and south of the equator. Now, as that happens, obviously, because it's sinking air, it's going to cause high pressure in those areas at 30 degrees north and south of the equator. And this is why we actually have deserts around these areas at 30 degrees north and south of the equator. So the areas here are generally hot and dry. And some of the air is going to be drawn back towards the equator, the cold air that sank down here, and the process is going to repeat itself. Now, that cycle right there is what is referred to as the Hadley cell. So the Hadley cell is revolving or moving heat from the equator towards 30 degrees latitude. Okay, so the rest of the sinking air, however, begins to move towards the higher latitudes here as warmer air in this particular area here, which is at the tropics. We said it's hot and wet, so some of the air now starts to move towards higher latitudes at 60 degrees. Now, as it moves there, it meets with cold air that is coming from the polar regions. Now, when that happens, the two air masses do not mix, but instead the warmer air will rise above the colder air. Now, as that happens, obviously, we know that it's going to cool down like it did at the equator as it rises due to loss of temperature. And it will then form clouds and you will have rainfall. And that rainfall is at, you'll have a high rainfall at a 60 degrees latitude. So that is going to create low pressure there. Now, again, the air now is cold up here and therefore cannot sink back down towards 60 because there is rising air at 60, and therefore some of it is going to be drawn back towards 30 degrees. Some of it is going to be drawn back towards the polar regions. But then if we are talking about this one here that is being drawn back to 30 degrees, it means that it's going to create high pressure again at 30 degrees and then be recycled around this area here. And that there again is a ferrule cell. So it's moving temperature or heat from 30 degrees toward 60 degrees north and south of the equator. So the rest of the cold air, we said, is going to be drawn towards the polar regions. And it's going to sink towards the North Pole and the South Pole in the southern hemisphere. Now, when that happens, it creates high pressure at the North Pole. As you can see here, the North Pole has high pressure. And that high pressure means that the North Pole is fairly dry. Okay, so some people say, oh, the North Pole has got ice. So why are you saying it's dry? But the North Pole obviously may have ice there because of its high latitude, meaning that it's getting less insolation, but there is no precipitation. There's not much precipitation there, and therefore that's why it's sometimes they're referred to as polar deserts. Okay, that's the global atmospheric circulation. So the next thing that the specification requires us to know is how to draw and to interpret climate graphs. So in this slide, we have a climate graph of Singapore. And to begin with, we can talk about what climate actually is. So climate is the average weather of a place over a long period of time. Now, normally records are kept of weather, obviously, and if you have a record of over at least 30 years, you can be able to determine what the climate of a place will be like, or the average weather of that place. And that is what is referred to as climate. Whereas weather is the day-to-day conditions of the atmosphere. So those are a lot more interchangeable. So going to the climate graph then, so if we look at the bottom part of the climate graph, if we find one of these in the examinations, then we'll need to be able to read this bottom part, which is the x-axis. And then we have two sides here. We have two y-axes. So one on the right here, which is representing the temperature, and then one on the left here, which is representing the rainfall or precipitation in millimeters. So the x-axis here is the months of the year, and then you have precipitation on the left here and temperatures on the right. But sometimes you may have temperature on the left and precipitation on the right. So you have to be careful and have a look at exactly what is being shown on which side. Then the other thing we need to note is the bars. Now you can see they're in a blue color here, and that's because they represent the precipitation or the rainfall. And if you want to read the highest rainfall, for example, you can see that the highest bar here goes up to here, and that is December. Sorry, that is being blocked by this down here. But yes, so in December, you can see that the precipitation, if we read it from this side, and go along there, is around 290 millimeters. And then for the temperature, that is represented by this line that is going across here. And that obviously is a red line to represent the temperature because it's heat that we are trying to represent here. And we can see that the highest temperature here is around May, right? So if we then look at how high the temperatures are in May, or the average temperature in May, would have to come across here to the y-axis that is on the right, and that's somewhere between 27 and 30. So we could, well, 25 and 30, so we could say that that is around 27 degrees Celsius. Okay, now overall, looking at this climate graph here, the temperatures actually we can see are fairly high throughout the year, actually fairly consistent throughout the year, and the rainfall is also fairly high throughout the year. And we can conclude from just looking at this climate graph here that this country is a country that is somewhere near the equator, because it looks like it's hot and wet throughout the year. And Singapore, if we were actually to look at the latitudes of Singapore, the latitude is actually 1.35 degrees north and 103.81 degrees east as far as the longitude is concerned. So 1.35 north latitude means that it's just slightly above the equator. So we can actually use climate graphs to give us an idea of where a country is located on that global atmospheric circulation model. We are now going to look at climate change, and our specification requires us to know about climate change from a historical perspective, as well as know about present climate change. Now, as far as causes of climate change in the past are concerned, we are going to start off with volcanic eruptions. So normally, if there is a large volcanic eruption, it's going to emit a lot of ash and dust, which will then go into the atmosphere. And as it moves up to the atmosphere, it will eventually get to the stratosphere, which is the layer above the cloud layer. And once there, that ash and dust is going to be spread around the world by very high speed winds. And as this happens, obviously, it's going to create a layer that is going to block or to stop some of the sun's light and radiation from getting to the earth. And that can lower the earth's temperatures. Okay, so and then now the second cause of past climate change in the past is asteroid collisions. So large asteroid collisions strike the Earth every 500,000 years, and the impact they cause blasts a lot of ash and dust into the atmosphere as well. And again, this has a similar effect to volcanic eruptions, because that ash and dust will then go up to the stratosphere and then be moved by those high-speed winds and block the sun's light and create lower temperatures. Now, the third one, or the third cause of past climate change, is the sunspot theory. So sunspots are black areas on the sun's surface, and they increase or decrease through 11-year cycles. So when we have more sunspots, the sun becomes a lot more active than normal, leading to higher temperatures, which means that during those periods when the Earth, when the sun has got a lot more sunspots, the Earth is going to be a lot warmer than the periods when the sun has got less sunspots. Okay, now the fourth one is the Milankovitch cycles, and these are changes to the Earth's orbit around the sun, and they can occur in three main ways. So sometimes the Earth's orbit can change from being circular to elliptical. Now, if you think about it, the circle will have a smaller radius or diameter, if you like, as compared to an elliptical shape, because an elliptical shape is a lot more oval. Now, obviously, when the Earth's orbit changes from circular to elliptical, then it means that the Earth may be either farther away from the sun or closer to the sun. And as a result, we are going to either have a warmer climate or a colder or cooler one. Then the second way within the Milankovitch cycles is the Earth's the Earth's axis can tilt. So the tilt of the Earth's axis. So it can tilt from being more upright to being, more on its side. And this again, when this again happens, some areas are going to be either farther away or closer to the sun, and as a result, you'll have either cooling or, well, cooler conditions or warmer conditions. Then thirdly, we have the Earth's wobble within the Milankovitch cycles. So when the Earth wobbles again, either you can have some parts of the Earth being farther away or closer to the sun, and as a result, you'll have either cooler or warmer conditions. So these three changes can lead to different amounts of sunlight being received here on Earth, and therefore the Earth either cooling or warming. So what evidence can we use to determine past climate? Now, the first type of evidence are tree rings. Now, this can be used to determine when we had warm and wetter periods, as well as when we had cooler and drier periods. So each tree ring will represent a year's growth in the tree's life. And if it's a thick ring, it represents a year that was warmer and wetter, which means that the tree experienced more growth because we know that the trees require sunlight and they require water. So if we have a lot more of that, then the tree will grow a lot more. And if that's the case, then it means that it's going to have very thick tree rings. And if the thinnest ring, obviously that was a cooler and drier year. And therefore, by using tree rings, we can determine what past climate was like. So the second type of evidence is ice cores. And we know that ice sheets have layers of ice that can help scientists determine or identify what the past climate was like. And the oldest ice is normally right at the bottom, and the newest ice is at the top. And each year, or each ice layer will represent 1 year of snowfall. And in the snowfall, we will have air bubbles that are trapped within the ice. And these normally can tell scientists about the amount of carbon dioxide in that particular air bubble, which will then help them determine whether it was a glacial or interglacial period. So a glacial period is like an ice age where the temperatures are really, really low. And then an interglacial is a warmer period that, like we are experiencing currently on the Earth. And if we have a lot more carbon dioxide in the atmosphere, then it means that that is likely to have been an interglacial period, which was warmer. Because we had obviously more carbon dioxide in the atmosphere. And then if it's a glacial period, then there's likely to be less carbon dioxide trapped within the ice. So the third type of evidence are historical sources. So historical sources in this case are things like drawings, paintings, and diaries, and these can be used to provide evidence for past climate change. And the historical sources that have been looked at so far suggest that climate changes every few hundred years, and that in the last 2,000 years, temperatures have varied between 1 and 1.5 degrees Celsius. So either colder or warmer than today's temperature. So they are a fairly reliable source when it comes to geographers and scientists determining past climate. So as we move on to present climate change, the first thing that we need to talk about is the greenhouse effect. So going to the diagram here, we can see that the sun's rays are coming down towards the Earth in the form of shortwave radiation. And when they get to the Earth, some of those rays or some of that heat is going to be absorbed by the Earth, and some of it is going to be converted into long wave radiation and is going to be reflected back up towards the atmosphere. Now, in the atmosphere, you have a layer of greenhouse gases that occurs naturally, and that layer of greenhouse gases will trap some of the heat that has been converted into long wave radiation here back towards the Earth. And that heat is what maintains the Earth's equilibrium in terms of temperature. So it creates a balance in the Earth's temperature, and that is what keeps the Earth's temperatures just right, because if we did not have this layer of greenhouse gases here, the Earth's temperatures would go to minus 18 degrees Celsius, which is fairly cold. So some of the heat obviously is trapped, like we've just said, and then some of it is lost into space. So what is causing a change in this natural greenhouse effect? So we have the effect of humans now, and the humans obviously are producing a lot of pollution. So human activities such as industry and transport is going to add a lot more greenhouse gases into the atmosphere, such as carbon dioxide and methane. And that layer of greenhouse gases that was occurring up here naturally is now going to be strengthened by this human activity that is adding a lot more greenhouse gases into the atmosphere. When that happens, a lot more of the heat that we talked about as being trapped in the lower atmosphere is going to be trapped, and a lot less of it is going to be to escape. And because of that, we then now have the enhanced greenhouse gas effect. And that effect obviously is an effect that has been caused by human reasons and is what is causing global warming. Okay, so what human activity is causing the enhanced greenhouse effect? So we'll talk about 4 causes here, and the first one is farming. So the world's population is growing fairly rapidly, and as a result of that, there is a demand for more food. And we know that when food is being grown, for example, rice paddy fields, those can produce a lot of methane, which is a greenhouse gas. Beef as well, in the ranches where cows are being kept, cattle is being kept for beef, we also have a lot of methane being released, and that is also a greenhouse gas that is leading to the enhanced greenhouse effect. Now, the second cause is industry. And we know that as people become more affluent in the world, the demand for manufactured products is also increasing. Now, those products are going to be manufactured in factories, and those factories are likely to produce air pollution, and some of the pollutants are greenhouse gases, and those again are going to lead to the enhanced greenhouse effect. Then the third cause is transport. We obviously know that a lot of people in the world now can afford cars, again, due to that rising affluence that we just talked about. And then there's increasing urbanization as well, as more and more people move into urban areas, get better jobs. And as a result of that, they can afford to buy a car. And a lot of those are combustion engine cars, which again are producing greenhouse gases that then lead to the enhanced greenhouse effect. And the last one we'll talk about here is energy. So energy, the way we produce our energy, especially our electricity in most parts of the world, is through the burning of fossil fuels. And if we are doing that, then it means that we are adding more carbon dioxide, carbon monoxide, and so on into the atmosphere, which are greenhouse gases. And again, those are leading to the enhanced greenhouse effect. So we'll briefly talk about the possible impacts of global warming. Now, one of the impacts is going to be frequent heat waves. Now, as the temperatures rise, obviously, that is something that is likely to happen, and that has its own negative effects. Then we have thermal expansion. So thermal expansion basically means that as the seawater heats up, it's going to expand, and that is likely to cause the sea levels to rise as well. And we know about ice caps melting. This is obviously, again, as a result of increasing temperatures, which is also likely to have an impact on the flora and fauna living in those areas where the ice caps are melting, affecting the ecosystems and so on, which also leads to rising sea levels as those ice caps melt. And we know that when we have sea levels rising, we'll have more intense storms, and that can lead to flooding in a lot of parts of the world. Then we are likely to have more frequent and severe storms. Yes, we've just talked about that. There's desertification as well, and drought. So areas that were just semi-arid may now become arid or fully desert. So people will not be able to grow food on them, and as a result, there's going to be drought, which is a condition where it's completely dry. Like you can see in the background here, the ground here is parched and therefore is cracking. So those are very dry conditions where food cannot necessarily be grown. and that leads to famine. Okay, I think we'll stop there on this slide and carry on to the next. So this next slide is a brief introduction on tropical storms. So what are tropical storms? They are rotating systems of clouds and storms that form over tropical waters. And once they form, they start to make their way towards the land. And this can sometimes have devastating effects. Then how do we classify them? We use the Saffir-Simpson scale. Now, as soon as a storm is categorized at, as soon as the wind speeds reach at least 119 kilometers an hour, it now becomes a tropical storm and can be categorized on the Saffir-Simpson scale. So the first category here, as you can see, is between 119 to 153 kilometers an hour, where you have some damage. Then the next category, extensive damage, devastating damage at the third category. And then fourth and fifth categories have got catastrophic damage. And like you can see that the wind speeds increase as you go up the scale. So what are their names, frequency, and where do they happen? So you can have a look at this map later on, or you can freeze it and have a look at it a little more closely. But they have different names in different parts of the world, but they are it's basically the same thing, just a different name in a different part of the world. So in Southeast Asia here, as you can see, they are called typhoons. In the south of Asia here and around Africa, they are called cyclones. And then in this region between Africa and North America, they are called hurricanes. So around America, they are called hurricanes. Asia, South Asia, cyclones, and typhoons in Southeast Asia. Now, where do they occur? They actually occur between 5 and 30 degrees north and south of the equator. And the reason for that is because there are warm seas there where you will have low pressure. And as you can see from the map here as well, the temperatures are over 27 degrees Celsius, which means that there's evaporation taking place here, or there's low pressure. And as a result of that low pressure, there's condensation and formation of clouds, which then gets the storm to begin to form. Now, somebody may ask why they do not occur right at the equator, because as we can see here, it's between 5 and 30 degrees and not 0 to 30 degrees. So around 0 degrees, 0 to 5 degrees, the Coriolis force is too weak for them to form, because we know that for these storms to form, the spin of the earth has got to come into play, and that spin of the earth is caused by the Coriolis force, which is very weak between 0 and 5, and therefore they do not happen right at the equator. So what are some of the hazards they bring? They bring strong winds, they bring heavy rain, they bring storm surges, and they also bring landslides. Okay, so how do tropical storms form? They require, first of all, three main conditions, and the temperatures have to be over 26.5 degrees Celsius to provide a source of moist, warm air, and that's why they form around the tropics. Then you also need 60-meter deep waters, and you also need the Coriolis force, which is the force that is created by the Earth's rotation. That is what causes the storm to begin to spiral and to spin and to move as well. And we can break down the formation of these tropical storms into a couple of simple steps here. And the first one is obviously those warm seas that are providing the moist air that then begins to rise. And as it rises, like we've seen before, it's going to create low pressure. And it leaves a vacuum behind it, obviously, as it rises and well below it, and that vacuum is quickly filled in by the air that is surrounding, rushing into that vacuum and creating very strong winds. Then as the air rises, it will cool down and condense and form big cumulonimbus clouds. And the condensation process as well is going to create latent heat energy, which will power the storm even more. Then thirdly, we have the Coriolis force. that now comes in as the air continues to rise. It will begin to spiral around the center of the storm due to this Coriolis force. And as it rises and cools, some of the air will descend through the middle and form a very clear and calm center. So that basically means if it's descending, that it's creating high pressure in the middle of the storm. And this particular part of the storm is referred to as the eye of the storm. So it's a center, and it's a lot calmer, and that is due to the descending air which has caused high pressure. Then fourthly, as the storm begins to spiral and move away from the source, it will pick up a lot more moisture as it carries along from the warm ocean waters, and will continue to grow in size as it moves towards where it's going to make landfall, if it ever gets there. And once it makes landfall, obviously, it's likely to create quite a bit of damage. But as it moves along the earth, along the land, sorry, it's likely to begin to dissipate. And the reason why it's going to dissipate is because there is no longer a source of warm, moist air to power it, and also it's going to experience quite a bit of friction. Because as you move along the land, you have trees, you have buildings, and those are going to create friction and slow down that spiraling process, and therefore dissipating the storm. Okay, so case studies. The first case study for tropical storms is going to be of an LIC country. So low income country, and that is Bangladesh, and its tropical cyclone Aila that happened in May 2009. Now this first map here shows the track. It tracks a storm, so it shows the path of this particular storm, and you can see that it began on the Bay of Bengal on the 24th of May and reached West Bengal, so western part of Bangladesh, on the 25th of May, and kept on moving up almost towards, as far as Nepal and Bhutan up here. So that was the path of the storm. Now, what makes Bangladesh vulnerable then? So Bangladesh obviously is a very poor country, and it's one of the world's poorest countries, and that's one of the reasons why it's so vulnerable, because if they get a tropical storm like this one, they are likely not to be as prepared as a richer country would be. Then the second reason why it's vulnerable, the country is vulnerable, is because it's very densely populated. Now, it's 60%, the country, Bangladesh, is 60% the size of the UK, but with 2 to 3 times the population of the UK. That means that, it's quite densely populated. And a lot of those people actually live in land that is very low lying, meaning that if there is a tropical storm, it's likely to affect a lot more people. So Bangladesh, 80% of Bangladesh is less than 10 meters below sea level, and 10% of Bangladesh is below 1 meter above sea level. And that means that if you have a storm surge from a tropical storm, that is likely to cause a lot of damage. Okay, so the next reason why Bangladesh is vulnerable is because it is at the confluence of 3 of the world's largest rivers. So a confluence of 3 rivers means that it's where these 3 rivers meet. So the rivers here that are in question are the Ganges River, the Brahmaputra, and the Meghna River. So they meet in Bangladesh, and because of that, and they are large rivers, because of that, there's a lot of water converging into Bangladesh. So as it is, you have that much water coming in through the rivers, and now if you have a tropical storm that then now brings a storm surge, then you have a lot more water that can then cause a lot of destruction as far as flooding is concerned. Now they also have the annual monsoon as well, which is a period of heavy rains, which adds a lot more into the mix. So what were the impacts of Cyclone Aila? Now, we can categorize these impacts into social and economic as well as environmental impacts. Now, it's important for us to know a couple of these because they can help us answer an 8-mark question if we were to get one in the examination. So the first social impact here is that 750,000 people lost their homes and had to migrate from their homes. So they were rendered homeless, and 90% of them actually were from the poorest or lowest income groups of Bangladesh, which means they were already vulnerable and now they had lost their homes. So recovery for them obviously is going to be quite difficult. And the second impact here we'll talk about is that there were 190 deaths. Then you have a large number of farm animals being lost and 1,000 acres of crops also being wiped out. Now we know that this farming is likely to be the livelihood of a lot of people living in Bangladesh, and this obviously is going to impact on the people quite a bit in terms of their income and the country's GDP as well. Then we have 200 kilometers of road either fully or partially destroyed. Now that is an economic impact because it's going to impact on trade. Goods and services are no longer going to be able to move in the country as smoothly as they were previously. Of course, before a kind of a normal situation is restored to the area. And also, if you're rebuilding the roads as well, it's going to cost money, and that again has impact on the GDP of the country. Moving on to environmental impacts, loss of animals in the area meant also a loss of biogas. Now we know that in Bangladesh, just like they do in India, biogas is produced from the animals, and as a result of that, with no biogas, it means that people now had to rely on woodland for firewood, meaning that they are going to cut down a lot more trees, and that then has an environmental impact. Then the second environmental impact here we are talking about is contaminated water, and that contaminated water was as a result of sewage coming onto the surface and mixing with the flood waters, and this spread diseases such as cholera and typhoid. And then the warm moist air as well brought about mosquitoes that then caused malaria within the population. And the third and last environmental impact here is that 30 Bengal tigers drowned. Now, these, as it is, are an endangered species, and the drowning of these tigers obviously had an impact on the environment. But you could also argue that, it's a tourist attraction, or the Bengal tigers are a tourist attraction, and therefore you could link that also to an economic impact because it would obviously affect tourism. So how does Bangladesh prepare for cyclones? Now, because Bangladesh is located in an area that is quite prone to cyclones, they have to do something to mitigate that threat of those cyclones. And they have used several strategies to do that. And we are going to look at 4 of those strategies, the first one being weather forecasting. So they have a meteorological department, obviously, in Bangladesh that issues weather forecasts and warnings through TV or on TV and on radio. And this has helped to lower the death rates, and especially during Cyclone Aila. The only problem is that not everybody has access to a radio or a TV, especially in rural areas where people are a lot poorer. And half of the population also do not own a phone. So if you were to try and warn them through the messages on their phone, then half of the people would not receive those messages. Then we have satellite technology, and this obviously is very expensive technology, and Bangladesh have to rely on satellite images from the US, China, and Japan. However, having said that, in 2012, the Bangladeshi government did announce that they were going to spend over $150 million developing their own satellite technology so that they can be able to monitor these cyclones themselves. Then thirdly, we have warning systems. So the government of Bangladesh again here educates people on cyclone warning signals, and they do this through meetings, posters, leaflets, films, and demonstrations, so that people know what to do if a cyclone was to hit the area, and therefore be prepared. And then lastly, we have evacuation strategies and flood defenses. So the country has invested a lot of money into evacuation procedures, cyclone shelters, and coastal embankments. So if we talk about cyclone shelters here, for example, we are talking about places where people can shelter, obviously, from the cyclones, especially the people that have houses that may be destroyed during a cyclone event. They can then find safety in those shelters. Then we have coastal embankments, which are raised areas, raised embankments that block water from flooding areas of Bangladesh. So those have been used as well. Now, have these strategies been effective or not? If you are to be asked, for example, in an 8 marker, to talk about or discuss, how Bangladesh prepares for cyclones compared to a country, say, like the USA, which is HIC. Actually, overall, Bangladesh have been successful in reducing the number of deaths and damage from cyclones through these mitigation strategies that they have used. However, there are still some challenges of some people not wanting to evacuate. The HIC case study that we're going to look at is Hurricane Katrina in the USA in August 2005. So this hurricane started as a tropical depression over the southeastern Bahamas. So if we look at the map, so it started around here, okay, and that was on the 23rd of August 2005. And on August the 24th, it became a tropical storm as it moved into central Bahamas. And then it continued to track west. Now, obviously, it's become now a tropical storm, and that's why now it's being categorized here and begins to move westwards. As it continued to track west, it got bigger and bigger with its initial landfall along the southeast Florida coast on the 25th as a Category 1, which obviously has wind speeds of over 120 kilometers per hour. Then it continues to move west across South Florida over the warm waters of the Gulf, gaining more energy and intensifying to a Category 5 around here as it moves northwest. And then that is on August the 28th. And then it weakened around here to a Category 3 before it actually made landfall, which you could say was sort of lucky because it would have caused a lot more damage otherwise. So it makes landfall then in the southeast of Louisiana and then along the Mississippi Gulf coasts. So how does the USA prepare for hurricanes? Now, please excuse the slide here. I've realized that it's reading wrong, the title of the slide. It should read, how does the USA prepare for hurricanes? So they use 4 strategies, and these strategies here are quite important because in an 8-marker you could be asked to compare hurricane management or hazard management in LICs and HICs. So these 2 case studies that we are looking at would be good ones to use for an 8-marker such as that. So the strategies that USA uses. So the first one we are looking at here is weather forecasting and warning systems. So again, the weather forecasts are normally quite frequent in the USA, and almost everyone has access to a TV, a radio, and a mobile phone. So in terms of communication, the communication of these forecasts is quite efficient. Then as far as satellite technology goes, again, the USA is a rich country and therefore they have an abundance of satellites with over 20 satellites. However, the satellites are getting old and some of them need updating. Then in terms of evacuation, the USA has identified areas that are at risk from hurricanes. You know, the ones that are considered now to be risk zones. An example being Florida. And such areas have warning and evacuation systems in place to help people leave the areas in case there's a risk from a hurricane hitting the area. Then finally, we have flood defenses. Now, Hurricane Katrina was one of the costliest hurricanes in the US, the history of the USA, and it really did test the protections that were in place to limit the damage from hurricanes. So, what were some of the effects then of this hurricane? It caused $108 million worth of damage, which is quite a bit of money. And obviously, that did affect the GDP of the USA. And the number of deaths was also quite high. So 1,833 deaths in Hurricane Katrina. Over 1.3 million people were evacuated. And 80% of those people were evacuated from New Orleans. However, some people were also left behind, and that could be something that would be criticized about the way they managed this hurricane. Then next, the levees, river levees were destroyed. So levees are sort of raised embankments that help protect the areas from storm surges and from river flooding. And obviously, because this was a huge storm surge, it destroyed the levees, leading to the flooding of New Orleans. So what has the USA government done to try and mitigate this then, or mitigate hurricanes? So they are now investing, or they have now invested in soft engineering methods such as beach nourishment. And beach nourishment basically involves adding sand to coastal areas, which means that if you have more sand, then you have a little more protection, because any waters that are coming in towards land are going to be slowed down by the beach material or the sand that has been put down. Then they also have wetlands, and those obviously are going to take some of the excess water and reduce on the amount of flooding there would be on the land as a result. And then they have artificial islands as well. And again, if you have artificial islands, these are going to slow down the water before it gets to before the storm makes landfall, and therefore reducing on the amount of damage. Okay, so that brings us to the end of this video. I hope you have enjoyed it and that you have found it useful. And I wish you all the best in your coming exam on Wednesday.